Hello, I'm John Joe, and this is the first lecture of a course that's going to cover the basics of Einstein's theory, the reason why he's so famous now, his ideas, and these ideas were revolutionary to what we consider, what we call the space that we move in, the space that my arm is moving. His ideas were revolutionary in this sense, and it provides some weird ideas about the space that we walk through. His second main idea is that these weird properties of the space also could explain gravity, why things fall to the ground. So this will be a very eye-opening series if you haven't already been exposed to this material before. And I'll say that I have it, so I made it so that a general audience could understand these ideas. So even maybe a 10 or 11-year-old, if they could use their imagination and they could think about these things. But the majority of this course I'll be using some math to get a more deep and a more precise understanding of these ideas. And the math I'll be using, I will assume Pythagorean Theorem. So ideally, uh, it would be best if you had some practice with Pythagorean Theorem, and I think the majority of students around the world, or at least I know in Chicago, they learned Pythagorean Theorem in 8th grade. So these lectures should be geared towards pretty much anyone in high school. There will be a couple points where, especially when we get to the gravity section, where in order to get a really deep understanding for the kids who have taken physics, I will mention some things that they might have seen in a physics class. If you haven't taken physics, do not worry at all. I will only mention these things and point them out. So don't be worried. If you see a math equation and you don't fully understand it, you will eventually understand it if you take physics in high school. But I won't spend too long on these features, just mention them. So please follow along and don't get too frustrated if you don't understand just the little things that will come that might pop up. But yeah, so anyway, let's get started. So I think my class is actually called the geometry of the universe, which we'll see that space and gravity is just a manifestation of the geometry. Um, so this is pretty interesting. I taught a class for droplet uh, with these titles. So special relativity, we'll see that this just means space, and the concept of space has a lot of we'll understand what relativity means, and then gravity is the proper name for it is actually general relativity. But when I was doing the course title for the last course I put, I just called it black holes because really all a black hole is gravity itself. So it sounds cool. I think people are more interested in the black holes. So if you're interested in black holes, then you will be interested in how things fall to the ground. Um, they're explained in the same way. So here's the table of contents. We don't need to spend too much on there, but I will just give a quick conceptual introduction, and then we'll follow with we'll introduce the math, we'll introduce the concept, and then we'll do some math, and then we'll reintroduce the concept with the math. So, like I said, the math is very easy. Do not be worried at all. Just you can follow through. You could pause if you want. So the next one is, like I said, general relativity just means gravity. So we'll cover some interesting things as we'll see. So okay. So what's so special about special relativity? Well, special just means it's a special case of gravity when there's no gravity, but um, But yes, this is our world is a very, very, very special place, and you'll see why right now. So I'm going to give a scenario where, let's just say it's today, in 2020, and we have two twins. If you're a girl, you could make this twin a girl, and then you could also have a boy or girl twin. But anyway, so let's just say you're 10 years old, and then your twin decides to go 18 million miles per hour on a spaceship journey. Okay, so this twin's going really, really fast. So then your twin comes back when you see 2070. So in your time, your calendar is 2070. You are 60 years old. Your 60th birthday happened, and then but when your twin comes back, he is only or she is only 40 years old. So this is weird. How could this be? You guys were the same age, and then you come back, and all he does is just travel through space, and then he comes back younger. So this is bizarre, and he actually only ages in this journey about 30 years. Really, this is an effect. So it's not just he perceives the sun going up and down. No, his clock is actually ticking slower because he's moving through space, and that is a weird feature, an important feature of space. And it has to do with the fact that space and time are in itself connected. So the more you move through space, the less you move through time. So we'll see this. So I would say, why does this happen? And then because the universe is four-dimensional, and so we see, sitting or standing, whatever we're doing, we could go left, right, and then forward, backwards, and then up, down. These are 3 dimensions. So 1, 2, 3. And then the big idea of Einstein is that time actually acts as a 4th dimension to the 3 that we already see. So not only can we move 3 ways, but we're also moving through time. All right, now we're moving. If you're staying still, you're moving through time. The most you could go. And then, since we treat it as another direction, we say, since the twin moves more through space, he moves less through time. So, just to give a picture of this, so let's for a second consider this. Let's just say like this is north and this is east. And we're going to say the two twins move 5 miles. Okay, so Gym 1 moves 5 miles north, and then Gym 2 moves 5 miles northeast. So because of this, because Gym 2 is moving east, he moves less through west, or he moves less through the north direction. So he's sharing his 5 miles with the north and the east, while Jim is only going 5 miles north. So obviously Jim is going to go farther north. Gym 1 is going to go farther north to Gym 2. Okay, so now since time is extra dimension, we see that if we look at this time, so Gym 1 is not moving through space, so he's moving 50 years through time, and Gym 2 is moving through space, so he's moving less through time. The exact same thing. This is a slightly inaccurate drawing. We'll see a little bit why, but pretty much light travels at this 45-degree angle, and then we'll see that nothing could go faster than light, and that is actually a property of space, and that's this is the space that we live in. This is why this weird thing that I'm moving my finger around is is causing me not to go faster than the speed of light. So, and causing this weird paradox. And this actually happened. So this the experiment was done there was a plane that went around the Earth really fast, and then there was a clock on the ground and a clock on the plane, and before takeoff, the clocks were synchronized, and then after the plane moved around the Earth pretty fast, the clock came back, and then it was actually behind in time by the exact same amount as Einstein predicted. So, and this happens even at low speeds. So even when we're driving in a car to the store at 60 miles per hour, this will happen. Don't expect to get any younger by doing this. So don't make this an aging strategy, because the effect is so negligible, but it actually does happen. So it happens relative to Gym 1 and Gym 2, of course. Where Gym 1 and Gym 2 are both on the Earth, and the Earth is moving. So we say that they're at rest relative to each other. So they're moving through the same space time. But then since Gym 2 is moving through space relative to Gym 1, then that's the effect. So that's why we call it relativity. It's just special and general relativity. We'll see why relativity even plays a role in gravity itself. So how do we make sense of this four-dimensional geometry? So this is the basics of the math we're going to use. So like I said, Pythagorean Theorem. I'll give a very quick review. So these aren't supposed to be squared. Sorry about that. So if you have a triangle, side length A, side length B, and then if it's a right angle, then we have C. The shortest distance between A and B from here to here, straight line, like it's a C, and the length of C is just described by the length of A squared, length of B squared, length of C squared. Okay, so let's see how this is used. So we'll just give some examples. If you already know of this, maybe you could skip this part and maybe go to the end of the lecture or fast forward. But if this stuff is unfamiliar to you, I will give a quick review. Or in fact, you should stick to it, just because I'll introduce some words we'll be using. So for example, I'm going to say, so this is home and school. We're going to say the school is 3 blocks east, 1, 2, 3, and we're going to call that dx. So we're going to call A, what we call A up here, we're going to write it as triangle x, because what we're going to say is we move in the x direction, okay? And the x direction here is just east-west. So x is the east-west direction. Cool. So now we could also say the school is 5 blocks north. So you could see that we call it the y. Like I said, we'll see this triangle actually just means change. So let's see, we have 1, 2, 3. So we start off at x equals 3, and then we go to x equals 6. So then this is x final. The ending position is x equals 6, and the starting position is x equals 3. So delta is the change between where you end and where you start, and that's how we could see, okay, so we start at 3, we end at 6, and then therefore we subtract 2, and then we actually move 3 blocks east. So the next direction is north. So we say, okay, so let's do this properly. So we start off at y equals 2. We start, put s start equals 2. We end at y equals 6. 6. And then, so our change in y is 6 minus 2 equals 4. And then, so our b, what we have b up here, is 4. And then, so we want to know, let's just say, the shortest distance from here to the school. Okay, that's not super straight line, but still, so how are we going to figure this out? What we're going to do a squared. We're going to use the a squared plus b squared equals c squared. So this is if you haven't had any applications to this, it's pretty interesting. So a is 3 squared plus 4 squared equals c squared. So this is 9 plus 16 equals 25 squared. The square root of 25, so 5 times 5 equals 25. So therefore c equals 5. Cool. So ta-da! Okay, so in this 2D world, so I drew this on paper. The grids were supposed to be even, by the way. These grids here, they're not so even. That is my bad. So we just say, let's just say this is even. So this could be even like 3 miles, 4 miles, and then we could either walk 3 miles east, and then we could walk 4 miles north. So we could walk 7 miles going this way, or we could just cut across here and walk 5 miles, being smooth. So if you want to get somewhere fast, always walk at this angle. You will shorten your distance traveled. You will shorten the length. You'll get there faster walking the same speed. So in this 2D world, like I said, we're going to call the c the ds. That's what we're going to call it. That's the total distance from A to B, from one point to the other, from home to school. And so, like I said, A, just to really bring the connection home. B, A squared plus B squared equals C squared. Okay, however, we don't live on paper, so there's a 3. I think I drew this from the other. I was using some Adobe thing, and that was difficult to work, so I switched to this new software, and then I recorded something and it wasn't happening. So let's just ignore these lines. So x, y, z, and then we draw the line. So this would be the ds. So all we're going to do, since we're adding a third dimension, pretty much we just do, we call this third dimension z. So dz squared. This is what we'll see right now. And then the whirler I see. So a more I don't know, let's say general example. If your friend is up on a hill, 5 meters high, and then you walk again, following the same example, 3 meters east, and then 4 meters north, and you have to walk up 5 meters, and we'll see that this is just 3 squared, the square root of 3 squared, the square root of 3 squared, 9 plus 16 plus 25. So that's the total distance from you and your friend in this 3D world. So now the whole weird effect of the twin paradox, where your twin being younger when he's going faster. So this, I just said that this happens because we live in 4 dimensions. So even though our eyes see this, we're moving in time as well. So how are we going to accommodate this? So what you might think is just how we add to the third dimension. We'll add time. But things are a little bit more tricky than that. So what Einstein showed, the geometry of our universe, is actually this. So this feature, I'll change it to red. Like I said, you see some annotations from the previous. What's happening? Okay, fine. So you can see some annotations from the other horrible. Let's see. Oh, I could delete these. Cool. Okay. The other software I was using that didn't have the proper drawing tools. So what Einstein showed is the geometry of our universe is this, and he actually said that this comes with a minus sign, and then this c is the speed of light. So like I said earlier, we can't go to the speed of light because of our geometry, and then this is how we or because of the space that we live in. So this is our geometry without gravity, by the way. So yeah, we include this c to get the effect of we can't go faster than the speed of light. We'll see this next time, but let's just think about why is there a minus sign. This is totally bizarre. How could you move in a minus a direction? You know, this is this is very weird. This is something to think about. Something that's not really too intuitive. You know, I don't. Yeah, it's very interesting to play with too. So actually, when you move more through time, you're actually moving a less total distance. So you could think about that. You could think about the speed of light. But for next time, we'll go over more. We'll end here, and then we'll see more of these weird properties of this geometry and why the geometry has to be this. So thank you for watching. This is going to get really fun really soon. So stay tuned. Thank you. Let's see.